I want to go over some stuff. First of all, I've had some questions, particularly about some of the assignments that I want to make sure to cover. And also, I want to go over some basics that I think in previous classes, previous semesters, when we got to this stage, that there was a little bit of misunderstanding about, a little bit of problem people have problems with on the exams and so on and so forth. So I wanted to make sure to cover those. Maybe that'll help out a bit. So before I go over those specific problems, let me lay a little bit of the groundwork. Okay, so basically what we've covered since the first exam includes the central limit theorem, right? We did the normal distribution. We worked with the normal distribution originally. We learned about the z-table, about z-scores, and so on and so forth. But then after that first exam, we started to talk about what happens when we take a sample from a population. So we learned about the central limit theorem. We learned about confidence intervals, right? And then we applied that in hypothesis testing. Hypothesis testing, and particularly where it involved numerical variables. Okay, in other words, where we were talking about means and standard deviations and so on and so forth. And that hypothesis testing typically involved a t-test. T-test is just a way to use what we learned about the way the central limit theorem works, about samples, very similar to what we were doing in calculating confidence intervals, but applied to comparing the means of two different groups. Okay, in some cases, we were comparing means, a sample from a sample from a population, the mean of the sample, to a known mean of another population, mu of another population. We call that a single sample test. Sometimes all we knew about the two populations were samples from the two populations, and that was an independent samples test. Okay, and also then we examined situations where we would be looking at kind of samples where we would measure something before and after some kind of intervention, right? So before and after a drug was given and so on and so forth. So we were looking at really one variable, which was a before value for each individual person, and one value that was an after value for each individual person or subject. And so we had two numbers, two variables, before and after, but we had a value but they were specific to each individual subject, this subject before and after, this subject before and after, and so on and so forth. Not two sets of individual people, one before an intervention, one after an intervention, but really the same people before and after. And that's called a paired sample test. And we understood that paired samples test was really what we were looking at was the differences before and after. So it was really a single sample test compared to the value 0, right? In other words, whether or not the difference between before and after was equal to 0, or whether or not the difference before and after was not equal to 0. There was a difference. In other words, attempt to prove that there was a difference because of the intervention. So I wanted to make sure that we kind of covered some of those basics. Okay, so when we were talking about confidence intervals, okay, when we talked about confidence intervals for a mean, a population mean, right, it's mu, okay, we take a sample from the population, and we're really interested in knowing what the mean of that population is. Unfortunately, the only way to know the mean of that population is to measure everybody in that population. But usually that's impossible. That's the reason why we take the sample, because we don't have the resources to measure everybody in the population. So instead of measuring mu, we measure x bar, which is the mean of the sample that we took from that population. Okay, if we know sigma, very rarely would we know sigma. Just like mu, it's something we really only know if we measure every in the population. If we know sigma, or if the sample size was very large, we made certain assumptions about this. And we said, well, we're going to calculate, even though we know that x bar is only an approximation on what mu is, the bigger the sample size is, the better we know it, right? So our confidence interval for mu, in other words, the range within which we expect the mu to fall, could be measured by saying x bar, the mean for the sample, plus or minus some score, some z-score or t-score. Talk about that in a second, times a standard error, right? Well, let's break this down a little bit. What is this standard error? The standard error is the variability of repeated samples of that size, whatever the size happens to be. And we know the standard error is equal to sigma, the standard deviation of the population, over the square root of the sample size. Well, that's very nice if you know what sigma is. But since we don't know what sigma is, we approximate it with the standard deviation of the sample, right, over the square root of the sample size. So if we know sigma, or if n was very large, right, we would use the z-score for the level of confidence that we wanted. And we know that for 95% confidence interval, we use the value 1.96. For 99% confidence interval, we use the value 2.58. And these are from the Z tables, as you guys probably remember. And for 90% confidence interval, we use the value 1.64. Okay, so essentially, if we knew what sigma is, or sample size is very large, say over 100, we would just use 1.96 for Z. If the sample size is small, we don't have a lot of confidence in our estimate for the standard error. So we use a different distribution, the t distribution. And for that, we look up what the t-value is for a specific sample size. And we get that from the t table. Okay, I'm going to just pull that up. You'll get a copy of this on the exam. I just happen to use Aggressively as the name of the textbook that I took the t table from. So I just happen to use that table. You can use any other table you want, including the one that's in our textbook. Right? Here's a t-table. So if our sample size is, say, 10, well, a sample size of 10 has 9 degrees of freedom, right? Degrees of freedom, sample size minus 1. So 10 minus 1 is 9. So 9 degrees of freedom. For a 95% confidence interval, we would not use 1.96. We would use 2.62. Well, what does that tell you? That tells you that the plus or minus, instead of 1.96 times our standard error, means 2.62 times our standard error. So we're adding and subtracting a bigger number from x bar, from the sample mean, than we would have been if we used the z-score. Also, if we had a bigger sample size, we'd be using a smaller value for t. Once we get over 100, we're very close to 1.96. So often we'll just use 1.96 instead. Okay, so that t-score varies depending on the sample size, the degrees of freedom. So we're going to add and subtract that. So naturally, our confidence interval, if our sample size is small, t is going to be big, and what we're going to be adding and subtracting from x bar, which we often call our margin of error, right? Our margin of error is going to be bigger. In other words, we have a wider range for our confidence interval. And what does our confidence interval mean? Our confidence interval tells us, 95% confidence interval tells us that we're 95% certain that the true mean of this population lies within the range of the confidence interval that we just calculated. Another way to look at that is if we took a sample from this population 100 times, if we took our sample 100 times, the sample size 100 times, and we got this confidence interval, well, we would say that 95 out of 100 times, the true population mean would be in our confidence interval, right? Or, in other words, you could also say 19 out of 20 times, right? So 1 out of 20 times, perhaps the true population mean will be missed by the confidence interval. Okay, so a 99% confidence interval, notice how big that number is, 2.58. 99% confidence interval is wider than a 95% confidence interval. It has to be wider because 99% means that you want to be more confident that you really have captured the true population mean in that range of two numbers. Okay, just as an aside, when we're dealing with the proportion, we do the same thing. For instance, if I told you that 600 out of 1,000 people were in favor of a gun control, let's say, right? You would say that 60% of your sample is in favor of gun control. Well, chances are when you surveyed that 1,000 people, that wasn't the entire population. It might be the whole population of New York State or Montana or whatever, right? So this is a sample just like any other sample. So the value P, the proportion that of the people that support gun control in that state, that's unknown, right? You don't know that. Just like you don't know, you probably will never know you'll probably never know what the proportion of people that support gun control in that state are. What you know is that 600 out of your sample of 1,000 support gun control. So you know P cap, just like you know X bar, you know P cap. You know an estimate of the population proportion. Okay, so if you know an estimate of the population proportion, just like here, you can calculate a confidence interval for your population proportion. So in this case, we usually only use Z. In other words, 1.96 for a confidence interval for a proportion. The reason for that is typically we're dealing with very large sample sizes when we deal with a proportion. So it's 1.96 times the standard error. Standard error proportions is calculated this way. The square root of P cap times 1 minus P cap over the sample size. Okay, all of that is underneath that square root. So if we calculate this, this would be 0.6 times 0.4 over 1,000, right? And we calculate that, and then we take the square root of it, and that would give you the standard error times 1.96, and we add and subtract that from P cap. So that's great. So now that we know about that, the central limit theorem tells us that we really can assume that we can predict that these intervals like this, because the central limit theorem tells us about how samples behave. One of the other things central limit theorem tells us is the central limit theorem tells us that as the sample size becomes larger, right, that it's less important. Initially, one of the assumptions that we make is that we're taking a random sample, right? Another assumption that we're making is that all of these people that are sampled in this population are independent. They're not related in some way. It's completely random. And we're also saying that we think that the population is approximately normal, or is in fact normal, right? Very close to normal. Well, the central limit theorem tells us that as the sample size gets larger, right? As sample size gets larger, we have a greater tolerance for the original population not being normally distributed. That doesn't mean that we don't want it to be normally distributed. It just means as the sample size gets bigger, our calculations become more reliable, even if the sample size, even if the original population is not absolutely normally distributed. However, one of the assumptions that we have is that it's at least approximately normally distributed. Okay, so now I wanted to also cover, before I go to specific problems, I also wanted to talk about this idea of hypothesis testing. Okay, let's talk about hypothesis testing. Okay, so in hypothesis testing, what we're doing is we're starting out with an assumption that we want to reject in order to prove a different assumption. So for instance, in hypothesis testing, one of the things I might be interested is demonstrating that the mean of one population 1, does not equal the mean of population 2. Well, that would be very nice if we just go directly to that, right? It'd be an interesting way to handle that. But usually, the way that we deal with that is we establish a null hypothesis as starting point, and then we establish an alternative hypothesis, right? And the reason we do that is because if we start with a null hypothesis, we can then establish what level of certainty do we want before we accept our alternative hypothesis. In other words, reject our null hypothesis and accept our alternative hypothesis. So we start with the null hypothesis and we say, we're not going to reject that hypothesis. We're not going to prove it. We're not attempting to prove that null hypothesis. But we're not going to reject it until we have enough evidence that there's less than a certain level of chance that we would be wrong in rejecting that null hypothesis. Right? So our null hypothesis usually starts out something like the mean of population 1 is equal to the mean of population 2. Of course, mean, since I'm dealing with means, we know we're dealing with population proportions, population numerical variables, right? So our null hypothesis is that the mean of population is equal to the mean of population 2. Notice I didn't say, how are we going to prove that now? The way we're going to prove that is we're going to take a sample from population 1, right? We can take a sample from there, and it's going to give us a mean, x bar 1, right? And it's going to give us, say, a standard deviation 1 as well. Population 2 is going to give us a different mean, x bar 2, and maybe a different standard deviation 2, right? Now notice our null hypothesis does not say x bar 1 is equal to x bar 2. That's not our null hypothesis. We're not really concerned about whether these two are equal. In fact, they'll almost never be equal except totally by chance, right? Because we're actually taking a sample of people. Even if the population had the same mean, that they're not likely to be perfectly equal anyway. But that's not what we're interested in demonstrating. We're talking about the populations and the mean. So our null hypothesis never says x bar 1 is equal to x bar 2, and our alternative hypothesis never says x bar 1 does not equal x bar 2. Instead, it says the mean of the population 1 is equal to the mean of population 2, and mean of population 1 does not equal the mean of population 2. This is called a two-sided test. The reason why it's called a two-sided test is because when we look at the distribution of all the sample means and we're comparing where one is to another, right? We're not, if this is the mean for population 1, right? We're not predicting whether the mean for population 2 is higher than population 1 or lower than population 2, right? We're not predicting initially here which one is the bigger of the two or the smaller of the two. You could do a single sample test where you might say the mean for population 1 is equal to or greater than the mean for population 2, right? Mu for population 2. And the alternative hypothesis is that mu is less than the mean for population 2, right? In other words, that's the only remaining possibility here, that mu1 is less than 2. Okay, so that's a one-sided test. You're predicting ahead of time that the only way that you could get this outcome is if the mean for population 1 is equal to less than the mean for population 2. You would need some sort of evidence that it couldn't be the other way. There's no possible way it could be the other way, where population 2 could be greater than population 1, that can't happen for some reason. And since we rarely get into a situation where that is the case, where it couldn't be the other way around, that you have evidence ahead of time that it couldn't be the other way around, this unusual situation, we usually stick with double-sided hypothesis testing like this. Okay, now the other advantage of this is that this is more conservative. Conservative. It's more conservative because if you look, if we're looking for 95% of the possible outcomes, differences between these two sample means or something like that, well, 95%, in order to distribute that so that we take advantage, so that we consider that the other mean could be lower and higher, right, with 95% certainty, well, then at each end here, this would only be 2.5%. So the value of that other mean has to be further away than if we did a single sample test where we said it can only be one direction. So all 5% is here, on one end. So the t-score, the z-score that we have to exceed to reject that null hypothesis is not as far as it would be for a double-sided test. Okay, but don't worry about that for now for this exam. Just keep in mind that's the reason why we're sticking with a double-sided test, and why that double-sided test is more conservative or safer than using safer in terms of like not making a type 1 error, rejected null hypothesis when you didn't have enough evidence to reject the null hypothesis, or when the null hypothesis is true. Okay, so there's a number of ways that we might look at this. In the situation where we're comparing the mean, in other words, if I told you we took a sample from population, first of all, I mentioned single-sided tests. Excuse me, I mentioned a single sample test, right? Situation where I have a single sample test. Let's say I told you that population 2 is known to have a mean of 110. Population 1, the mean is unknown. And the only thing we know about the mean is that we've taken a sample, we found X bar, and we found the standard deviation, and X bar was equal to 100, and standard deviation had some value, let's say 10 or something like that. Well, in that situation, we've taken one sample, and we're comparing the mean of that sample to the known value of the mean for the population 2. Okay, the way we would phrase that for a null alternative hypothesis is just like before: mean of population 1 is equal to mean of population 2, and the alternative mean of population 1 does not equal the mean of population 2. But in this special case, we know what the mean of population 2 is. So instead of writing that, we could typically write this: equals 100 and does not equal, I'm sorry, equals 110 and does not equal 110. Right? That's another way that we could write that. Okay, this is okay for a two-sided test, right? Where we or two sample tests where we have two samples, one for each population. Okay, now, okay, so let's take a look at that t-test. Take a real quick look at that t-test, and then I'll move on to these other problems. Okay. So when we look at our hypothesis test, there's a few different ways that we might run into a hypothesis test. One way is that single sample test, right? Single sample t-test. Okay, and our null hypothesis is going to be that mu1 is equal to, say, 100, and mu1 is not equal to 100, right? H null and H alt. Right? So now, how do we actually go about proving? How do we actually go about proving that? Well, we calculate a t-score, and t is going to be equal to X bar minus the known mean, which is 100, over the standard error. And where do we get this from? T is equal to X bar. X bar is the sample mean from the sample that we took. Say the sample size is 50, and X bar turns out to be 90, and the standard deviation turns out to be let's say 5. Okay, so t is going to be equal to X bar, which is 90, minus 100 over the standard error. How do you calculate standard error for single test? Standard error is equal to standard deviation of the sample, because that's probably all we know about, but we don't know the population standard deviation, over the square root of the sample size, which is going to be 5 over the square root of 50, right? Whatever that comes out to be. I'm going to take a wild guess. 7 times 7, 5 7, it's going to be around 5 7, so it's about 7 7 49, 7 5 7. It's going to be about 0.8, let's say. It's going to be something like 0.8. Okay, so that's going to be over 0.8, right? So we'll calculate a t-value. I'm sorry I made it that big a number, but say t-value I'm gonna make believe that this was really 98. The t-value comes out to, I don't know, roughly 2.4. Well, at this stage, we would say to ourselves, for this size sample size 50, what is our t-value for a 95% confidence interval? In other words, 5% chance of being wrong. In other words, alpha equals 5.05, right? What would be that value? Well, I go to my t-table for sample size of 50. Sample size of 50, or 49 degrees of freedom, that would be 2.01. And so our t-value for that sample size would be equal to is going to be equal to 2.01. That is called our critical value of t. That is the value of t that we would need to achieve in order to reject the null hypothesis, to be at least 95% certain that it's okay for us to reject the null hypothesis. In other words, have less than 5% chance that we would get this extreme of value, difference between the means, if the null hypothesis were true. Okay, so since this is our t calculated is bigger than our t critical, 2.01, we reject the null hypothesis and accept the alternative hypothesis. Well, a single sample test is pretty easy because a single sample test makes it easy to calculate standard error and use the standard deviation from the sample. Now, if we have a two-sided test, things get hairier. Two sample hypothesis test. It's called two-sample hypothesis test. Two-sample hypothesis tests things get considerably hairier because your sample sizes for group 1 and group 2 could be different. Say the sample size here is 64, and the sample size here is 32. Your means that you get are going to be different. Say this is 12, and this is 10. Okay, and your standard deviations can be different. Okay, let's say this is 7. And let's say this standard deviation is equal to 13. Let's make it a little bit bigger, 16. Okay, so we have an issue here. We have two different means. Well, okay, well, our t-tests are null hypothesis, right? H null and H alt is going to be mu1 equals mu2, population 1 mean and population 2 mean. Mu2 does not, and be specific here. In other words, if this is hospital 1, the mean for hospital 1, don't put mu1, I'm just writing that down in general. Put the mean, identify what it's the mean of. Otherwise, somebody reading this wouldn't know what you're talking about. Just call it 1 and 2, and it's really hospital 1, hospital 2, or diabetic ward and some other ward or something like that, right? So mu1 equals mu2, or mu1 does not equal mu2. Okay, so there's no alternative hypothesis. What level of error are we willing to accept? Well, usually it's 5%, could be at times 1%, right? So now how do we calculate our t-value for this? Well, okay, our t-value is going to be, we don't know what mu is, so instead it's going to be x bar 1 minus x bar 2 over the standard error. Okay, well, that's clear enough. X bar 1 we know, x bar 2 we know. Okay, standard error. How do we calculate the standard error? Well, the standard error, it gets a bit more complicated. Depending on whether the standard deviation of this group is approximately the same or equals the standard deviation of this group. If these two standard deviations if one is not double what the other is, we assume equal variances, and we use a special set of formulas. That's on that table that I gave you in class. We use a special set of formulas to calculate what the standard error is. And we actually, if they're not equal, you do a first step, you calculate a pooled standard deviation, and then use the pooled standard deviation to calculate what the bottom of this equation is. And if you guys remember, it's something like SP times the square root of 1 over n plus n1 plus 1 over n2. Right, it's the whole bottom of this equation. That's the standard error. What's in the bottom of that equation is the standard error, but you have to calculate the pooled standard deviation first. Well, in this case, the standard deviations are not the same, right? One is more than double the other. So here we assume that the variances are not equal. There's a second page there where you can use to calculate the t-score and this formula. Actually, a little bit simpler. You can calculate this formula to determine whether or not what the standard error is and what the p calculated happens to be. Okay, and then you could also figure out what your degrees of freedom. In the case of pooled standard deviations, is equal to n1 plus n2 minus 2. And in the unequal variances, right, this other case that I didn't illustrate here. In this other case, the degrees of freedom are very complicated to calculate. So typically, most people just take the smaller sample size, subtract 1 from it, and use that as the degrees of freedom to find your p critical. And if your t calculated is greater than p critical, you can reject the null hypothesis. Okay, but you'll have to go back there and take a look at that and get a gander at it and work with it a little bit. Okay, so now I want to address one other thing which we covered last week, which was ChiSq. And I just want to, there might be one question on ChiSq, or one question with a few different answers on ChiSq. But I just wanted to remind you that the way ChiSq is calculated, okay, well, first of all, we need a null and alternative hypothesis. Chi-square is used where chi-square, odds ratio, relative risk are used in situations where we're dealing with categorical variables. Okay, and when we're dealing with categorical variables, often one of them may be an exposure, the other one might be an outcome, like a disease. Okay, so let's say the exposure is excessive alcohol consumption, and no exposure is no alcohol consumption. Okay, and the outcome is, let's say an injury or no injury. Okay, so in this situation, we're looking at a situation where, for instance, in a particular population, let's say we have we're in the emergency room, we're surveying all the cases, a sample of all the cases coming to the emergency room, and we're analyzing 100 cases, 50 of them that involved alcohol consumption, 50 that didn't, and whether or not let's say a head injury was involved or something like that. Say in the case of alcohol, we found that 10 out of the 50 involved alcohol, people consuming alcohol had a head injury, and with no alcohol, it was 8 out of 50, 42 didn't. Right? Well, we'll see that 18 out of, and this is 82, right? That the prevalence of head injuries in this population was 0.18 or 18%. Right? Well, we can use that 18% to create another table, which is the values that we would have expected, from a population of 50 people, 50 alcohol drinkers, and the outcomes, right? Injury or no head injury. Right? The outcome we would have expected is that 18% of this group who had consumed alcohol, or 9 people, would have had a head injury, and 9 people out of this group would have had a head injury. And how do we know that? Well, the overall incidence is 18%. So if there was no reason to think alcohol contributed to this, we'd expect the same rate, the 50 people to be expected at the same rate that were alcohol consumers as the people who were non-alcohol consumers, right? This is our observed values. These are the expected values that we have. But we know we can calculate chi-square by taking each one of these boxes, 10 minus 9 squaring that value, and dividing it by the expected values. In other words, that would be 10 minus 9 squared over 9. And then we would do that for each subsequent box. So we get 4 numbers, add up all those 4 numbers, and we would get a value. I'm going to make up a number, 3.97. Okay, chi-square is equal to 3.97. Well, that number represents a calculated value of chi-square, calculated value of how extreme the differences are between the observed values and what we would have expected. The bigger this number is, the more likely that the differences are not due to chance. So what's our null and alternative hypothesis here? A null and alternative hypothesis is H null is going to be that there is no association between alcohol consumption and head injury. Okay, and our alternative hypothesis is that there is an association. In other words, the risk for head injury is the same, and the risk for head injury is different. In other words, there is no association, and there is an association between alcohol consumption and head injury. Okay, so this value 3, we have to know. Well, okay, we calculated a value of chi-square based on the formula that we worked on in class. How do we know if it's big enough to reject this null hypothesis? Well, just like the t-test, we go to a table which gives us the chi-square values. Okay, let's see if I can't find it real quickly. Here we go. Here we go. Okay, let's take a look at this chi-square. Whoops. Let's take a look at this chi-square table. For a probability of 0.05, in other words, an alpha of 0.05, for whatever number of degrees of freedom. Well, how do we calculate degrees of freedom here? Okay, and I'm not to keep from killing time. I'm going to tell you how to do it rather than try and pry it out of you like I normally do in class. But the degrees of freedom in this case is going to be equal to the number of rows minus 1 times the number of columns minus 1. Okay, and in this case, there's 2 rows minus 1, so it's 1 times 2 columns minus 1 times 1. Okay, so the degrees of freedom are equal to 1. So I'm going to bring this back up here. And for 1 degree of freedom, the critical value is 3.841. So our critical value, chi-square critical, is 3.841. So our calculated value of chi-square is bigger than our critical value, meaning that it's large enough for us to say that we can reject the null hypothesis and accept the alternative hypothesis. Okay, well, what about these other things? Odds ratio and relative risk. Well, relative risk is, let's see, the risk of people at drinking alcohol get a head injury is 10 out of 50, right? That's equal to, let's see, 10 out of 50 is 0.2, right? And the risk for people who don't drink alcohol is 8 out of 50, which is 0.16, right? So the relative risk is 0.2 over 0.16. And that comes out to, I'm going to say something like 1.25, something like that. Something of that nature, close, I'll say 0.2. So 1.25 more times more likely to have a head injury if you are drinking than if you're not drinking, right? So that's called our relative risk or risk ratio, because the risk is a ratio of the 2 risks. Well, what is our null hypothesis there? Our null hypothesis there is that the risk ratio is equal to 1. In other words, there's no difference between the rates for those 2 guys, right? Or our risk ratio is not equal to 1. And how do we determine whether or not we can reject the null hypothesis? It depends on whether our confidence interval is different enough for us to reject the value of 1. So in other words, if the confidence interval for this 1.25 is 0.9 to 1.3, we can't say that it's not 1, so we can't reject the null hypothesis. But if it's 1.1 to 1.3, 1 is excluded, so we can reject the null hypothesis, accept the alternative hypothesis. For the most part, when we do this, you'll be using SPSS to do this problem. We did it in class. I think you can go back and take a look at the recordings on that. And I think I also did a help session on that also, where we actually calculated as well. So the odds ratio works a little bit differently. The odds ratio is the injured over the non-injured. So in other words, the odds of being injured, the odds if you drunk alcohol of injury, the odds are 10 out of 40, right? 10, the number of people that had an injury, versus 40, the number of people that didn't have an injury. 10 out of 40, and for people who didn't drink alcohol, it's 8 over 42. So the odds ratio is 10 out of 40 over 8 out of 42. So it gives you a slightly different number than 1.25, but it's a similar. It also gives you a fraction. So this is 0.25 over. I don't know what that's going to be. It's going to be 0.30. Let's assume. So this might be 1.3 instead of 1.25. So it's going to give you a similar result. But again, your null hypothesis odds ratio is equal to 1, or the odds ratio is not equal to 1. And it's going to depend on whether or not the confidence interval for your odds ratio, which you calculate with SPSS, includes 1 or excludes 1. If 1 is not inside the confidence interval, you can reject the null hypothesis. If 1 is inside the confidence interval, then you can't say that your result is different than 1. In other words, no difference in risk for alcohol consumers versus others. Okay, so just so we had that kind of sewed up. Okay, so I want to get to those particular questions that came up. Okay, and particularly on assignment 5B. Okay, so let's open that up. Okay, so while I'm opening this up, how are you guys doing online? I haven't seen any commentary in the background there. Have I lost you guys? Okay, good. You're still there? All right, good. Glad to hear it. All right, so okay, let's take a look at this. The ones that came up there was one issue here. Investigator, I think a little bit of problem with the phrasing on this. State your null and alternative hypothesis, and you could really only, there's actually both of these, your null and alternative hypothesis. I really should have corrected that. I didn't correct it because so many people have already started answering it. But your null hypothesis, it's SAT scores, the mean of the sample, X score 624, mu of the population is equal to mu of psych students, your null hypothesis, mu of the population not equal to mu of the psych students is your alternative hypothesis, right? So I'm going to just make that so everybody gets scored correctly on that. But the top two are the null and the alternative hypothesis. So for whatever that's worth. Can we have some examples of the calculations of what we just discussed on ChiSq? Sure. Let me get through this because I know some people were particularly interested in a couple of questions here. 15, okay, came up quite a bit. Let me see if I can't clear this up here. Okay, I think I can. There we go. Let's take a look at 15. Okay, 100 male and female infants is tested to determine their distance and systolic blood pressure with the following SPSS table. So in this case, I rather than give you a SPSS file to do a calculation, I've actually given you the output table. Okay, so I'll do that sometimes when I'm a little reluctant if I'm concerned that like the machines might not be that reliable in class. So you might get a file that you need to do the analysis on, or I might give you tables like this in the exam. So 100 male and female tested determined the difference in systolic blood pressure. Based on this result, you should assume variances of the two groups. Here's our result down here. Okay, based on this result, you should assume the variance of these two groups is the answer equal or unequal. Let's take a look at this. What's the standard deviation for males and the standard deviation for females? 11.8 and 11.145. You guys remember what the rule was for that? If the standard deviation of one group is not double of the others, we're going to assume equal variances. And we're going to pool our standard deviations, pool our samples for our standard deviation. So this, we're going to assume that they're equal, right? There's more evidence of that. If you go down here, this part of the t-test, right? This up to this line, notice the t-test starts after this vertical line. From here to the right is the t-test. These four boxes here are part of a test for the equality of the variances. The assumption is that, just like any null hypothesis, that the variances are equal is assumed. In other words, that's our null hypothesis. We only reject our null hypothesis if our probability of being wrong is rejecting it is less than 5%. In other words, if this significant is less than 0.05. So this tells us stick with equal variances. Use equal variances. This and this both agree to stick with equal variances and use the top row for our t-test. Okay, so next it asks us the value for t in this test is, what's the value for t in this test? The value for t in this test is here, 0.607, right? It's actually looking for a string, 607, to give you to mark it correctly. And what is the p-value? What's the probability of being wrong if we reject the null hypothesis? In other words, the two-tailed significance. The degrees of freedom is 98. Remember, degrees of freedom was equal to the two sample size and 1 plus n2 when it's equal variances. Then 1 plus n2 minus 2, which is 100 minus 2, which is 98. What is the significance? Probability of being wrong if we reject the null hypothesis? It's 54%. What's okay? So the p-value is 0.545. This suggests that we should, well, if the probability of being wrong is bigger than 5%, this is way bigger than 5%, what should you do? Well, you should fail to reject the null hypothesis. And you should type in that whole phrase, fail to reject the null hypothesis, into this box. Okay, so let's take a look at the next part here. The mean gestational age of infants born to mothers who smoke is compared to mothers who did not smoke with the following result in SPSS. Now again, here we have the tables. In this case, standard deviations again are very similar. So we assume equal standard deviations and look at our significance here for our equality of variances is bigger than 5%, so we use the top line. The t-value for this analysis is, in this case, it's 4.476 with a p-value, a probability of being wrong if we reject the null hypothesis, of 0.001000. It's really 0.00, less than 0.001. It's not really zero, but SPSS doesn't go beyond 3 places here, right? So it's way less than 5%, so we reject the null hypothesis. We put 0.000 here. The total size of both groups is 100, right? Is 100. Okay. Based on this result, and they didn't ask for degrees of freedom there. They asked for the total size of both groups, right? Which is 98 degrees of freedom. And you know it's 100, and also you can just add these two together. Based on this result, we reject null hypothesis. So you would type in reject into that box instead, right? So that's the way we would deal with that particular problem. Okay, so now let's take a look at our chi-square situation. Let me just make sure before I leave the page. Let me just make sure there's some other stuff. Okay, question 15 and 16 we just did, I think. Okay, 5b, 10 and 11. Take a look at 5b, 10 and 11. 10 and 11. Okay, calculate the standard error. Okay, 5b. A study was conducted to determine if expected mother cigarette smoke has an effect on bone mineral content. Samples 73 newborns whose mother smoked have a mean bone mineral content of 0.99 with a standard deviation of 0.026. A sample of 161 newborns, bone mineral content of 0.91 with a standard deviation of 0.025. Assume that the variances of the underlying populations are equal. And in fact, we probably would assume that anyway, since the standard deviation was 0.026 and 0.025 for the two groups. State your null hypothesis. The mean for smokers equal to the mean for non-smokers, mean bone weight density. That is, I really should have made that more specific. Mean bone weight density for smokers, it's not equal to the mean bone weight for non-smokers, right? You would expect that. Calculate the pooled standard deviation for these two groups. Well, how would I do that? Okay, let me just do that one first. Okay, remember what the pooled standard deviation was. Let's see, pooled, whoop, 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 I don't need that. Away. Okay. I think I turned that off. Pooled standard deviation. Well, let me pull up that sheet that I gave you for that. I think I call it t-test variations. Okay, t-test. There it is. See what this one looks like. Okay. Well, it looks a little funky, doesn't it? But it's really not that hard. Let me wait for Word to let me move this around. Here's our formula. I'll just echo our formula here. The pooled standard deviation is the square root of sample size 1 minus 1 times the standard deviation for group 1 squared plus sample size 2 minus 1 times the standard deviation for group 2 squared over n1 plus n2 minus 2. Okay, so our pooled standard deviation in this case is equal to, let's write it all in there. The sample sizes were 77 and 161. So n minus 1 is 76, right? And n2 minus 1 is 160, right? Times standard deviation of group 1 was 0.026. And we're going to square that. And for group 2, it's 0.025. And we're going to square that over the combined sample sizes minus 1, which was 77 and 161, was 241. No, 230, 231, 238. 238 minus 2 is 236. So tell me if I'm wrong. Okay, I think it's 236. Now let's see. This should be these two added together, which is 236. Okay, good. So now we would just simply have to work this out. Okay, so if I get my calculator up here, okay, so 0.026 times 0.026 is equal to this times 76 equals 0.0514. I'm going to call it. Let me pull this down a little bit. 0.0514 for our purposes. Plus, now I'm going to do the second part of this here. 0.025 times 0.025. Okay, 625, that looks right. Times 160 is equal to 0.1. 0.1000 over 236. Okay, so our pooled standard deviation is equal to Say clear 0.1514 over 236 equal to that. And then I'm going to take the square root of that whole thing. It's equal to 0.025. Pooled standard deviation is equal to 0.025. Right? Actually, it's a little bit more than that because, as you can imagine, it's halfway between, it's a little bit of the way between 0.025 and 0.026. That's the bigger sample size because it's actually closer to 0.025. Okay, a lot of work for not much of a difference, right? So, okay, so let's see. We want to know the standard error, right? Calculate standard deviation. Oh my goodness. Standard deviation, the pooled standard deviation, we got that. Then calculate the standard error. Well, the standard error is what's going to be under our t value. T calculated is going to be x bar 1 minus x bar 2 over the pooled standard deviation times, right? Where's our sheet there? Where did our sheet go here? Let me find our sheet again. I think I have it here on the word. Pull it back up again. Here it is. So what is our standard error? Our standard error is everything that's underneath here. So it's our pooled standard deviation times the square root of 1 over n1 plus 1 over n2. That's going to be equal to times the square root of 1 over n1 plus 1 over n2. Okay, that is our standard error down here. Okay, so if I calculate that, I'm going to clear. Okay, so that is going to be, that's 1 over 77. And I'm going to put that into memory. And plus, I'm going to clear that. I'm going to combine that with 1 over n2, which is 1 over 161. Equals to this. I'm going to add that to memory also. I'm going to clear that. Let's see what if I recall that. Yep, that worked. Okay. So that, I'm going to take the square root of that whole thing. That's equal to 0.139. 0.0139 is going to be what's inside the square root. And I'm going to multiply that by our pooled standard deviation, which is equal to 0.025. And hopefully that'll give us our answer, which is equal to 0.0035. Okay, so on the bottom there is 0.0035. That's our standard error. And we're going to divide that into the difference between the two means. What was the difference between the two means? Now, finally, we're on the home stretch here. What was the difference between the two means? The difference was 0.99 minus 0.091. Right? So that's going to be 0.099 minus 0.091 over 0.0035. Hopefully you'll keep an extra digit or two to make sure that there are no rounding errors. I'm trying to do this as quickly as I can. So it's 0.008 over 0.0035. And that's going to be equal to, I'm going to clear memory. I'm going to put this into memory. I'm going to clear this out. I'm going to put 0.008 divided by, I'll recall that, it's equal to 2.31. So our T calculated is equal to 0.231. 2.31. Okay, so now what is our critical value of T? Well, for such a big sample size, our degrees of freedom are N1 plus N2 minus 2, right, which is going to be 236, I think it was, right? 236. So such a big sample size, we know that our T-score probably going to be pretty close to 1.96, right? What our z-score would have been. It actually might be 1.97 or 1.98 or something like that. It's going to be pretty close. So we can see, because this is so big, 2.31, it's bigger than our critical value, calculated value t is critical. We got our critical value t, we can reject our null hypothesis that the bone densities for the two populations are the same, and except the alternative hypothesis. Did I give? I might have given you an actual data file for this as well. So if I gave you an actual data file, it would save you a lot of trouble, because then you could just use. Let me just see. Let me go back to Blackboard, see if I actually gave the data file for this. Okay, let's see. Let me go back here. Okay, assignments. New page. Okay. Preliminary. No, I didn't give you a data file for that particular one. Right? I gave you one for a different problem. For that was probably in 5A or something like that. Right? So yeah, you were forced to do that manually. Hopefully, maybe I'll be a little bit more reasonable and give you a data file for it. So you can just use SPSS to actually solve the file, similar to the other ones we did before, similar to the ones that we saw on questions 15 and 16, where you get that output table. Okay, now, you mentioned that you were interested in seeing a solution for a chi-square problem. Okay, so one way that so if I go back to that, if I open up a new chi-square test, okay, we've got a data file I can use. Let me see if I have a data file I can use. The variables are here. Alcohol consumption, scalar, no good. I need categorical variables. Yep, numerical and nominal. Nope, scalar. Nope, it's not going to do us any good. Heart rate, not likely. Let's see a good one here. Let me back up here. Let's see, that's a PDF file. Nope, numerical. Numeric. Wait a second. Oh no, that's actually, yeah, nominal and nominal. Okay, let's take a look at this one. Waiting for SPSS to open, hopefully. So I'm going to use SPSS to solve this problem. Okay, I will explain as I go through it. I will explain how we would have solved this manually. Nope, I'm not interested in that. Uh-oh, okay, didn't like that file for some reason. Come on. Let me try opening this again. Attempt to connect to remote server failed. I don't know what that is. Deviation scheme. Don't know why it's not cooperating. Let me try this. Open. Oh no, I'm not able. I'm not in SPSS right now. Jeez, what's the problem? What's the problem with this? Okay. Open data. And navigate to it, see if that helps. Open. Let's see if it's happy with it now. Oh, something may be happening here. Here we go. Okay, so here is a set of data, and it's smoking status for pregnant women and whether or not they had a premature birth. If I look into the variable view, I can see that this is both nominal data, okay, and 0 represents the mother smoked during pregnancy, 1 represents the mother didn't smoke during pregnancy. And over here, 0 represents the infant was premature, and 1 represents the infant was not premature. So I am going to go back here, and I'm going to create a crosstabs table from this data. Notice this is pregnant woman number 5, pregnant woman number 7, and this particular one, she smoked, and the infant was premature, and so on. So let me analyze this data. I'm going to say analyze, and I'm going to go into descriptive statistics and crosstabs, because I wanted to summarize this data in a 2x2 table. In other words, did the mother smoke or not smoke, and was the infant premature or not premature? So I'm going to go into descriptive statistics crosstabs, and I'm going to ask it to create a table for me. I'm going to go into cells and ask it to create the observed values for me, and I'll click OK. Whoops. First, I have to tell it that in the rows is the exposure. The exposure is smoking. And in the columns is the outcome, premature baby or not a premature baby. Okay, so let's take a look at our outcome. Okay, so here's our outcome. The mothers who smoked during pregnancy, we had 114 women that smoked during pregnancy. 18 of them, in 18 cases, the infant was premature. Mothers who did not smoke during pregnancy, 76 were premature out of 684. Okay, so overall, we had 94 premature births out of 798. It's kind of hard to tell what's going on there exactly, because 76 and 684, there's more here, but it's a much bigger population, right? So we're interested in figuring out whether there's an association between mother smoking and premature births. So our null hypothesis here would be that there is no association between whether a mother smoked during pregnancy or and whether there was a premature birth as a result. Okay. Our alternative hypothesis is that there is an association. So there's a few ways we can prove this. We're going to use this is categorical data. We're going to use chi-sq to prove this. How would we use chi-sq in this case? Well, first of all, we would calculate the prevalence overall in this population, 94 out of 798. So if we looked at that, let's say that's 12%. If we looked at that and we said to ourselves, well, if there's no difference between whether a woman smoked or not, we would expect 12% 114 births to be premature, and 12% of the 684 births to be premature. In other words, at the same rate as both groups together. Right, so we would create an expected values table. We can do that in here. You can do it by yourself, or we can do it in here. Descriptive statistics, crosstabs again. And we could go in here and tell it in cells, create expected values as well. Okay, and click OK. So now our expected values, SPSS happens to put them in the same box as the observed values. So our observed values was 18. If there was no association, we would have expected only 13. And what about the mothers who did not smoke? Well, we would expect 80 premature births, but there were fewer. So it looks like not smoking is protective here, doesn't it? It looks like smoking puts the infants at risk. The question is are these differences big enough for us to reject the null hypothesis? So how do we calculate the chi-square value mathematically? We take, for each box, we take the observed value minus the expected value, square it, divide it by the expected value. In other words, 18 minus 13.4 over 13.4, that gives us one number. 96 minus 100.6, square that difference, and then put it over 100.6, that's our second number, and so on and so forth for each of these four boxes. Add them all together, that gives us our chi-square value. If our chi-square value is bigger than our critical chi-square value, for a 2x2 table, you remember we said that was 1 degree of freedom, and the value was 3.841 from the chi-square distribution table, right? That's how we would calculate that. We can also calculate our odds, our risks. A risk, if the woman is pregnant, the risk of a premature birth is 18 over 114. The risk for mothers who didn't smoke was 76 over 684. The relative risk is 18 over 114 divided by 76 over 684. Now, how about odds ratio? The odds for mothers who smoke was 18 over 96. The odds for mothers who didn't smoke was 76 over 608. And the odds ratio was 18 over 96 divided by 76 over 608. That's our odds ratio. Well, fortunately, SPSS can do this for us. I'm going to analyze descriptive statistics crosstabs. I'm going to go into statistics, and I'm going to ask it to calculate chi-square and these risks for me. I'll click OK, and let's see what SPSS gives us. Okay, so our chi-square value, which is the same thing you would get if you calculated it mathematically the way I described it, is 2.054, and it's 1 degree of freedom as we predicted. Okay, is that big enough to reject our null hypothesis? Well, we know critical value of chi-square was 3.84, so this is too small for us to reject our null hypothesis, so we fail to reject our null hypothesis. How about our odds ratio? Oh, well, if we go down here, our odds ratio is 1.5. It looks like the odds of 1.5 times is great for women who smoke for having a premature baby. But do we have enough evidence of that? Is our 95% confidence interval, does it tell us that we're 95% sure that even though we calculate 1.5 times, that it's not different, that it's not, that it can't be equal to 1 with 95% confidence? Well, let's see, 95% confidence interval is 0.85 to 2.1, 2.6. 1 is between those. So we can't say with 95% confidence that it's not 1. Had this been 1.8 to 2.6, we know then that we're 95% sure that the true odds ratio is not 1 because it was outside of the confidence interval for what we think the true odds ratio is. This second line is your relative risk. Similarly, the relative risk seems to be 1.4 times as great for smokers, right? But we didn't have sufficient evidence to reject the null hypothesis because confidence interval does not exclude a relative risk of 1, right? Because it could be 1 because 1 is inside the confidence interval. Right? So at any rate, so hopefully that helps. So I'm going to call it a night. You have another night. If you have another chance to submit some more questions on Blackboard, if you get a chance between now and Tuesday morning. For those of you that are online students, I'll get in touch with you in terms of if you want, the exam is going to be published on Blackboard. If you want, if you're an online student, and you have the time available, you may take the test simultaneously with the students that are taking it in class. If you need to time shift it, get in touch with me, and we'll assign a time window for you to take the exam. So on the exam, central limited chi-square. Yes, yeah, basically that's it. Everything from the last test, basically, right? Which I think that pretty much covers what we did since the last test. Central limit theorem, a confidence intervals, t-tests, and a little touch, one last question on chi-square. Just stuff that we've introduced on chi-square. I actually put an assignment up on chi-square. It's not due until next week, but you could, if you want, you could give it a try as a backup.